16 miles until the service stopped. Miles and miles of black straight roads.
Dan Olds here, and we are at Los Alamos National Lab, and with the eminent Gary Grider, who's been involved in HPC since what'd you say, 1981?
Correct.
And you've been to 29 of the 30 SCs.
That's correct.
Which is incredible, and you're going to the next one.
I will be there.
Okay, I will.
Saturday.
Too. You driving?
No.
You want to ride with me? Stop by Sandia?
No.
Oh, no.
There's not a lot between here and there.
So you've seen a lot in your career, and I guess I just want to start with a broad, open question. Where do you see HPC going?
Oh, that's a good question. So, HPC is gone a lot of directions in the last 30 years, but it's interesting right now. The exascale project is interesting.
Yes.
And they're doing a lot of funding and building a lot of machines. It's kind of unfortunate that the machines that they're building are all really highly well suited for dense arithmetic, dense algebra, LINPACK. But other kinds of applications that are well suited in that environment, machine learning and things like that are typically pretty dense, pretty easily parallelizable. And the pieces that are harder to tackle aren't being tackled very well, in my opinion. Mm-hmm. Dense or non-dense, sparse, irregular, very, very hard problems.
And more like an HPCG then?
HPCG is a good approximation for streams, so it's a good approximation for memory bandwidth. And yes, so
it's a sparse matrix, isn't it?
It is a sparse matrix, but it's not necessarily all that irregular, and it's not multiple pieces of physics going on at once, and so it's a baby step towards a representation of a real simulation. And if you look at the machines that are being built, they're maybe 1% efficient on HPCG.
Yes.
And so we're buying exaflops worth of machines, and we're getting petaflops worth of actual use, right? Which is scary, right? It's a big deal. If you're, there are applications that get 20, 30, 50, 90% use if they're dense, and they're pretty regular. They're very parallelizable. But if not, and it's kind of diminishing returns and has been for a while. We're designing machines today for workloads, for subsets of workloads of the future, I think, right?
Okay.
I mean, machine learning and is the memory version of Hadoop in a way, right?
Okay.
It's very parallelizable, the training phase at least. And there's no huge dependency graphs, or at least not yet. Eventually they may get there. And so I think we're building machines how we know how to build machines.
Okay, that's a better way.
And we're trying to figure out how to make software run on them well. And some software will, mm-hmm. and some software may never run very well on them. And so where do I think HPC is headed? I think one path of HPC is absolutely headed in that direction, full speed ahead. And lots of money and lots of big machines are being built for that. And that's not a bad thing, it's just a thing. Mm-hmm. I think that what we're trying to do here is actually go the other way. So we're actually trying to figure out, okay, instead of building machines how we know how to build machines and pounding the software into making it work on them. That's one version of co-design, right? I redesign the software to work on whatever hardware I know how to build.
Sure.
Another version is to try to build hardware slightly different to mate up better with the application. And so that's the approach we're taking, and we are almost unique in that regard right now.
And with Sierra being the latest example of that?
Sierra is a Livermore machine.
Oh, I'm sorry.
And what is Sierra? Sierra is a big GPU machine.
Yes.
And what's it going to run really well? It's going to run dense applications really well, right?
True.
And so, frankly, there's a difference between our workload and Livermore's workload. Livermore's workload, they do an awful lot of V&V and quality assurance and those sorts of things, which end up being ensemble type calculations. Mm-hmm. And so it is quite parallelizable. And so it may be a good machine for them. It probably won't be a good machine for us because we actually, certify 75 or 80% of the stockpile. So almost all of our applications are simulation and not necessarily verification kinds of applications. We do that verification too, but the mix is really different from here to there. And so we typically run a big calculation on half of the machine, a petabyte of memory for 6 months. Wow. We're probably the only site in the world that does that. Go to Oak Ridge, they've got a petabyte of memory too, but they would never give it to a single application for 6 months. They can't do that. They're an Office of Science site, they've got to give time to everybody, right?
6 months for a single app with a petabyte of memory.
Yes, 24 hours a day for 6 months to get to an answer.
Yeah.
And in fact, that problem we had been trying to run for the last decade. We tried to run it on Cielo and it wouldn't run. We tried to run it on Sequoia, which was a Blue Gene machine at Livermore for a long time. We never got anywhere there. We finally ran it on Trinity. We finally got a machine built big enough with enough memory and enough, the right kind of architecture to run it. And frankly, it's an important problem. And you know what we learned by running that problem? We're 10 times too small to even figure it out. Wow. So we need a 10 times bigger footprint memory machine. And we need to run the job for 6 months on that machine. Of course, we don't own that machine. Hopefully someday we will. And so at any rate, our workload is different. And every site's workload is slightly different. And because ours is the preponderance of what we do is these very large scale simulations that have at any one time 10 to 20 physics packages running simultaneously inside the application. There may be multiple link scales going on. Some of it may be running at molecular level and some of it at continuum level, all in the same application, all at exactly the same time, right? So it's highly irregular. And so trying to pound those kinds of applications into a dense linear algebra, embarrassingly parallel mechanism just is not in the cards. We'll never get there.
So your standard CPU, GPU, it's a bad fit.
Well, the GPU at least.
Okay.
CPUs are much better at being interrupted.
Yes.
Right? They're much better at speculative processing. They're much better at those kinds of things. And so right now, it's looking like CPUs are kind of the answer for us.
For you guys. Yeah.
However, even CPUs aren't really wonderful because their memory bandwidth is so crappy, right? And I mean, the memory bandwidth per amount of flops is, it's 1/10 of a byte per flop. How many bytes per flop was a Cray 1? 3 words, 24 bytes per flop. 2 64-bit quantities coming in and the 64-bit quantity going out. 3 words every cycle. How many cycles? I mean, now it's like 0.1 bytes per flop. That's the memory bandwidth into a modern day processor. And of course, they've got big cache.
Compared like that.
Oh, it's god awful.
Incredible.
It's incredibly bad.
Yeah.
It's horrible. And our applications, because they float over the entirety of memory. There's no hotspot. We need to sweep over the whole memory every time, right? And so we get really, really crappy efficiencies, just horrible efficiencies, because there's not enough memory bandwidth. And that's the first sin. And so we've got to fix the memory bandwidth problem. So that's what we're going to go after. The other piece that's very important is latency. What happens when you get a miss? You're going through and then you hit an indirect reference in the code, and that's not a thing you want to multiply. That's an address of somebody else. You've got to jump somewhere else in memory to get the thing you want to go multiply with, right? Indirect references like that. Well, if you think about these really icky codes that have 30 physics packages and stuff, they're going to want to use a lot of indirection to make those programs tractable.
Sure.
So there's a ton of indirection in the codes. And so every time you turn around, you've got to face a latency hit. You know how many cycles you waiting for a latency hit? Thousands.
Wow.
So you're at 0.1 or 0.01% efficient during that piece of the code simply because you're hopping around in memory, grabbing, locations, right? We're not unique in that particular problem. That problem manifests itself in large-scale graph problems too. But nonetheless, that's where we live. We live in this world where we need memory bandwidth more than we need flops. And we need memory latency fixes more than we need flops. Memory bandwidth can be fixed. You can throw money at it. You can use HBM. You can move the memory closer to the processor. There's all kinds of things you could do. 3D integration. And so there's things you can do about memory bandwidth. With memory latency, largely that's physics. You can only go so fast.
So, yeah.
But there's tricks. And it turns out they're old tricks. Scatter-gather engines. Scatter-gather engines were big on Cray X and Ps and Y and Ps. Why? Because codes had indirection in them, and you needed to put specialized hardware that would go, and you would give it a list of addresses, and it would go gather up the things from memory and hand you a dense thing to go do your multiplication or division on, right? And so that kind of stuff is where we need to go. So anyway, so we're working really hard over the next decade for our next couple of big machines to be highly efficient. Instead of being 0.1% efficient like we are today, probably, we'd like to get up to 10%. That would be amazing to our users. And so we don't necessarily want a big machine here. It's not that we don't want a big machine, but we don't care.
It's an efficient
We
machine.
want a lot of science. Because we got a lot of science to do. Because if I got to run one problem for 6 months to get an answer on half of a machine, that's how, I mean, and it's 10 times too small already. I need a lot of, I don't think I could ever have that many watts in this county. I'm not sure I could have that many watts in the state, right? Wow. We got to do something about efficiency as a community, and we're the stalking horse for that because our applications drive us there. And so that's what we're doing. I wouldn't say that's necessarily where the whole industry is going, because there's this huge shiny object machine learning and shiny object AI, which are great stuff. And going to do.
Really solve your problem.
It does not solve my problem. Now, it's not that I can't use those tools. For example, people are looking at how to use those tools to guide the application.
Yeah.
So you could use them maybe to analyze the output of the application, but physics you can't do with machine learning. You got to do it with simulation.
Yeah.
And simulation sometimes is really icky, hard, and big, nasty simulation. That certainly defines what we do. And there's not a substitute for that.
But it's good you're pulling the industry in a direction of fixing the memory bandwidth problem.
Well, so that's actually helps everybody.
Yes.
I mean, everybody's waiting on memory bandwidth.
And that's the thing that I had some luminary tell me many years ago, that if you're doing HPC correctly, the last hurdle you're going to hit is memory bandwidth. And you're not going to fix that one. Someone else has to fix that one.
That's why Cray ones were awesome.
Yeah.
They had, you got a result every clock.
Mm.
You read in 264-bit floating point values, you did a multiplication, and you wrote out one every cycle. That's unheard of today, right? You're lucky to get 1/100th.
Yeah, more cores don't fix that.
They don't. They only fix it if you can turn. They help you because they generate more addresses to look up. Mm-hmm. But when you run out of memory bandwidth, you're out of memory bandwidth.
Yeah.
And each core can't keep the memory busy. A single core can't keep the memory busy because it can't generate addresses fast enough. But several cores can, and when you run out of memory bandwidth, you're out. Yes. That's all there is. And modern processors today are hovering around 0.1 bytes per flop. I mean, that's incredible.
And even the processors with more memory bandwidth, that still isn't changing that ratio very much. I'm thinking about like the power processors, the
a little
AMD.
A little.
It's a little bit.
A little bit. For example, the new AMD has 8 memory channels instead of 6.
Yeah.
So, yeah, it's better. It's better by how much? Well,
it's like a 25%.
25% better.
Something like that. Yeah.
You're still off by 4 orders of magnitude.
Yeah.
Right? I mean, so it's great. We love it. Bring more of that.
That's what you can get now.
But
you want that.
And GPUs actually use HBM, soldered on HBM right next to the processor. So they get a 4x, maybe a 5x. Of course, the only way to use a GPU is data parallel. And so if you cast your problem that way, it's great. But if you can't use that. And actually, there's an interesting story about GPUs. The first machine on the first top 500, or the top machine on the first top 500 list ever, was here, right over there in a building. It was a CM5. Danny Hillis actually lives in Santa Fe. The thinking machine CM5. And the thinking machines was the first machine, I believe, that was ever programmed using data parallelism. Data parallelism is SIMD, same instruction across lots of data, right? It's massively parallel. And so that machine is kind of where, and its predecessor, the CM2, was where data parallel programming started. And it became what is now the common GPU, and CUDA is essentially a SIMD language that evolved from C star and things like that, which came from thinking machines. So we've been there, back in the 90s. We were playing in that space. And in fact, we even coupled our CM5 with a YMP,
Okay.
which was a predecessor to a modern day CPU and GPU put together.
Yeah, it's like a traffic.
They were each quarter acre size machines that were glued together, which is not what we do today, right? It's all glued together in one machine. But it's fascinating, right? That was already been done a long time ago. It just wasn't done inside of a node. It was done in two separate rooms with a big wire between them. Same concept. You use a CPU for what you use a CPU for, and you use a GPU for the mass parallel thing. Same thing we were doing. We were using the CM5 for mass parallel SIMD operations, and using the Cray for all the integer ops and all the stuff that
It's like a friend of ours, mutual friend Henry Newman, says, there are no new engineering ideas, just new engineers.
Yeah.
That discover
Right.
these old ideas that worked quite well in the past.
Yep. So anyway,
Great stuff.
Interesting
Well,
stuff.
thank you so much.
sure,
I really appreciate the time.
no problem.
I got